Section 3.4 covers something that we've already done. We're just going to put a new name to it, and that is an instantaneous rate of change. The derivative is an instantaneous rate of change. So the derivative evaluated at some point will be the limit as h approaches 0 of f of x at that point plus h minus f of x over h. This we learned in previous sections was the derivative. In section 3.4 we learned a shortcut for the derivative, and from here on out we will use the shortcuts for the derivatives to evaluate derivatives. In example 1, it says the volume V equals 4/3 pi r cubed of a spherical balloon changes with the radius. So the radius is going to be our variable in this problem. And do you remember the different notation we have for the derivatives? There's no need to review that. Okay, so right here, this is our variable in this formula. The question then is, at what rate does the volume change with respect to the radius when r is equal to 2 feet? The first thing we need to do with this problem is find the derivative of v with respect to time. By finding the derivative of v with respect to time, we can find the rate of change. If v is equal to 4/3 pi r cubed, what is dv dt going to be? First of all, you've got to remember pi is a constant here. Do you remember the power rule for taking derivatives? Let me write it down right fast. The derivative with respect to x of x to the n is n times x to the n minus 1. Our variable here is r. So dv dt, I'm going to use v prime if that's okay with you, is equal to 4/3 pi times what? 3r squared. Can we simplify this at all? 3 cancels out with this 3 right here, doesn't it? And we end up with v prime is equal to 4 pi r squared. When the radius is equal to 2, because that's what we were told here, the rate of change of the volume of the balloon is equal to what? It's 4 pi times 2 squared, which is 16 pi. Now this is going to be cubic feet per foot, because the units of the derivative here will be the units of the volume divided by the units in foot. So when the radius is 2 feet, the volume is changing at a rate of 16 pi cubic feet per foot. Part B says, using the rate from Part A, by approximately how much does the volume increase when the radius changes from 2 to 2.4 feet? How are we going to figure this out? By approximately how much does the volume increase when the radius changes from 2 to 2.4 feet? Do you understand the question? We're looking at a rate of change. As r changes from 2 to 2.4, this is a change of 0.4. So we end up with our volume that we had from the previous problem is equal to 16 pi cubic feet per foot. And then we multiply this by this rate of change of r. So that would be 0.4 feet. So we take the rate of change of volume when the volume is 2. It's changing at a rate of 16 pi cubic feet per foot. And as we increase the radius from 2 to 2.4, this is an overall change of 0.4. Do you see what I'm doing here? So if we multiply the rate of change times that 0.4, what do we end up with? 0.4 times 16, that's 4/10. That'd be 6.4 pi, which is approximately 20.1 cubic feet. The units go to cubic feet because if you use unit cancellation here, this is the rate of change of the volume, or this is the amount of increase of the volume. We're going to get into more detail with these whenever we start looking at related rate problems. They'll be a little bit easier to understand at that point in time. Now, this brings up something that we're going to be looking at. This difference right here that you see in the velocity, the instantaneous velocity formula, the numerator of that is actually called the displacement. The displacement of an object over time is just the difference in the y values of that object, the y values of the function. The average velocity then is the displacement divided by time traveled. The displacement represents a distance. The velocity is distance divided by time. So That's where we get this formula from, which happens to look an awful lot like a derivative, doesn't it? The definition then for velocity is it's going to be the derivative of the position with respect to time. So typically we use s to denote the position function. The velocity then is the derivative of the position. Speed is the absolute value of velocity. And this, I remember, this is what we were talking about. The question had to do with what is the speed of an object that was falling. So once we found the velocity, we had to take the absolute value of that. And acceleration is the derivative of the velocity. Let's take a graph of, I believe this is a velocity graph. The velocity graph of a particle moving along a horizontal line that was discussed in example 2 in the book. As long as the velocity is positive, the object is moving forward. And that's pointed out right here. And then once again, we have a positive velocity. So let's look at example 2 that has to do with the graph. By the way, when the velocity is 0, what does that mean? The object is stopped. And in order for an object to go from forward to backward, at some point it has to stop, even if it's just for a split second. In example 2, it says the accompanying figure shows the velocity. So this is a graph of the velocity of a body moving along a coordinate line. Part A says, when does the body reverse direction? That means going from forward to backwards or backwards to forward. When does the body reverse direction? At t equals what? 2, because the object is going forward when the velocity is positive. Once the velocity switches to negative, the object is then going backwards. At t equals 2 and at t equals what? When is it moving at a constant speed? Meaning it's not increasing or decreasing in speed. From 3 to 6. T equals 3 to 6. Part C says graph the body's speed for t equals 0 to 10. If we're going to graph the body's speed, first of all, it's moving forward at a constant rate. Then it reaches a maximum velocity. And then it starts to decelerate. But it hasn't gone backwards yet. So we need to look at the graph choices here. Remember, we're graphing the speed. Are speeds ever negative? Speeds are never negative. So we can automatically cross out A and C as choices, can't we? So we can cross out choices A and C because this is the graph of the speed and it's never negative. So then we have to choose between these two graphs. And then looking at this, we see that our acceleration is going from positive to negative. So we're going from forward to back. But at some point, this object has to stop. The question is, at what point does the object have to stop? And that is at x equals 2 and at x equals 7. So we look down here and we see, do we see graphs at x equals 2? We have a stop. 2, this doesn't stop. And at 7, we stop. And this one looks like it does stop at 7. No, it doesn't. It reaches a maximum at 7. This graph choice can be knocked out because the speed has to be 0 at these points right here. The speed has to be 0 when the object changes from forward to backwards. So the correct answer choice is D, because this. It's impossible for an object to go from forward to backward without being having a speed of 0 at that point at which the direction changes. And this is a graph of the velocity, and we were looking for a graph of the speed. Basically what you do is you take the graph of your velocity and flip this negative part up. Part D says graph the acceleration where it's defined. Acceleration is the derivative of the velocity. This is the order in which things progress. We have the position function. The derivative of the position is velocity. And the second derivative of the position function is the derivative of velocity, which is the acceleration function. So in part D, when we're asked to graph the acceleration, I'm looking for the graph of the derivative of this function. The derivative of velocity, we said that derivatives are slopes of tangent lines, right? And this velocity function is made up of a bunch of straight line segments, isn't it? Well, guess what? Your slope of a straight line is a constant function. So the acceleration graphs have to be slopes of, it has to be a collection of constant functions. So automatically we can toss out B as a choice because it's going to be a bunch of line segments. Now, when the slope is going up on a line, our derivative is going to be positive because this is increasing. The slope of an increasing line is going to be positive. So from 0 to 1, we expect to have a positive value. Well, that crosses out C as a choice because here between 0 and 1, the function is negative. So we eliminate this as a possibility. All right, this slope happens to be 2. From 0 to 1, the slope happens to be 2. So if I were to graph the acceleration, I would be looking at a constant function right here at 2. Here between 1 and 3, our slope is negative 2. So we would be looking for a function with a slope of negative 2 here. When our derivative is a constant, when the function is a constant, what's the slope of a constant line like this? 0. So we expect to look at this. Do we see any of these graphs taking shape? Yeah, which one is it? This is the correct answer choice here. So you see how you look at the graph of the function and then identify what the graph of the derivative would look like. Example 3 says the equation for free fall at the surface of a celestial body in outer space is measured in meters per second, is s equals 1.49 t squared. So this is the position function. How long does it take a rock falling from rest to reach a velocity of 22.7 meters per second on this celestial body? How long means we're looking for what variable? We're looking for t, when v of t is equal to 22.7. Now, we said that the velocity is the derivative of the position, so we're going to take the derivative of this, and that is the velocity. What's the derivative of 1.49 t squared? 2.98 t, because you bring the 2 down and then you subtract 1. So we set this equal to, and we're plugging that in place of v, right? So we have the equation 2.98t equals 22.7. So to solve this for t, we're going to divide both sides by 2.98. And this is why God gave us calculators. And we get t is equal to what? Seconds, because our time was measured in seconds, right? All right, example 4. It says a rock thrown vertically upward from the surface of the moon at a velocity of 12 meters per second reaches a height of this. That's our position function. So our position function is s equals 12t minus 0.8 t squared. Part A says find the rock's velocity and acceleration at time t. If this is the position, how do we find the velocity of position? And that's going to be 12 minus 1.6 t. Acceleration is the derivative of the velocity, which is the second derivative of the position, which is negative 1.6. It's a constant. This is the acceleration due to gravity on the moon, measured in meters per second. B says, how long does it take the rock to reach its highest point? How are we going to figure out how long it takes the rock to reach its highest point? If we toss a rock on the moon, no matter where it is, it follows a trajectory like so, right? Its highest point is going to be right here, isn't it? Where we have a horizontal tangent. So the highest point is where the velocity is equal to 0. Set the derivative. Well, the velocity is the derivative of the position function. So in order to answer B, we need to take the velocity function and set it equal to what? So our velocity function is 12 minus 1.6t. We set that equal to 0. Subtract 12 from both sides. Negative 1.6t equals negative 12. Divide both sides by negative 1.6 and we get t is equal to what? So t is 7.5 seconds. Part C says, how high does the rock go? Well, how are we going to determine how high the rock goes? Find S of 7.5. And that'll tell you the position or the height of the object. So we look at, I'm looking at the position function here, right? 12 times 7.5 minus 0.8 times 7.5 squared. And once again, this is why God gave us calculators. We end up with S equal to what? 45, approximately. I'm pretty sure that's right. What will the units be here? Meters, because this is the height. Part D says, how long does it take the rock to reach half its maximum height? Well, if this is the maximum height, what do we want to solve to find out when it's half the maximum height? Find T when S equals half of 45. We'll just do it that way. So we go to the position function, and we set it equal to 22.5, and that was 12 times T minus 0.8 T squared. What type of equation is this? This is a quadratic equation. How do we solve quadratic equations? Set it equal to 0, right? Good job. So this is going to be 0.8 T squared minus 12 T plus 22.5 equals 0. Do you remember how to solve a quadratic equation? It's negative b plus or minus the square root of b squared minus 4ac all over 2a. What is a equal to in this problem? 0.8. B is equal to negative 12, and c is equal to 22.5. When you plug this into your calculator, you're going to end up with two answers. One of them is t equals 2.2. The other one is t equals 12.8. How can there be two different times when we're at this height? Well, the plus or minus, but also if this is halfway, don't we have one where the object is going up and then another time that the object's at this height when it's on the downward trajectory? So this is when the object's moving up, and this is when the object is moving down, that we have this height of 22.5 meters. Just a little bit of algebra thrown in here. Part E says, how long is the rock aloft? How do we determine how long the rock is? You didn't need calculus for that one. This one you could have done with algebra. So we're going to solve 0 equals 12t minus 0.8t squared. What's the first thing we need to do here? Right, factor out a t. Good job. Now what? T times 12 minus 0.8t equals 0. Now what? Right, set each factor equal to 0. We end up with t equals 0 and 12 minus 0.8t equals 0. T equals 0 is when the object is on the ground before we project it into the air, kick it or whatever. What do we get here? Add 0.8 to both sides. 0.8t, divide both sides by 0.8, and we get t is equal to 15 seconds. It takes 15 seconds for the rock or whatever it is to hit the ground again. So in summary, the position function is s of t. The velocity is v of t, which is the derivative of s of t. Acceleration is a of t, which is the derivative of the velocity, which is the second derivative of the position. You see how we're just progressing here? And then we have something called jerk. And if you've ever ridden a roller coaster, you know what jerk is. It's when you quickly change acceleration or direction. And that's j of t, which would be the derivative of the acceleration, which is the second derivative of the velocity, which is the third derivative of the position function. And remember, speed is the absolute value of the velocity. All right, in the last example, we're going to get some business terminology. One of the things you need to know is that whenever you take the derivative of a function, it's also called a marginal. A marginal is the derivative of a function. All right, suppose that the dollar cost of producing X appliances is given by this cost function. A says find the average cost per appliance for producing the first 140 appliances. To find the average cost, we use a bar over a variable to denote it's an average. This is going to be the cost of producing 140 objects divided by 140 objects. The average is the number that you produce divided by the number that you have. So this is going to be what? 1,400 plus 130 times 140 minus 0.3 times 140 squared. divided by 140. Remember to put the numerator in parentheses or hit enter to get a total on top before you divide by 140. We end up with $98 here. Part B says find the marginal cost when 140 appliances are produced. The marginal cost, I said, is the derivative evaluated at that point. So to find part B, we use the derivative evaluated at 140. So looking at the cost function up here, we're going to take the derivative. So we look at C prime of X is going to be what? Derivative of 1400 is, derivative of 130X is, and the derivative of negative 0.3X squared is 0.6. Negative 0.6X. So the derivative evaluated at 140 is going to be 130 minus 0.6 times 140. Okay, and when we punch this into our calculators, what are we going to get? I believe it's $46. This means that when you produce 140 items, your rate of change of your cost is going to be $46 per the next item produced. Okay, so that's the rate of change of the cost when you produce 140 items. Part C then says show that the marginal cost when 140 appliances are produced is approximately the cost of producing one more appliance after the first 140 have been made by calculating the latter cost directly. Let me translate this question into English for you. Essentially, it means find the cost of producing one more appliance beyond 140. To figure out what the cost of producing the 140th item is going to be, we're going to be looking at the cost of producing all 141 items minus the cost of producing 140 items. What that does is that'll give us the cost of producing the 141st item. Does that make sense? Because this cost is a cumulative cost, and I want to know what's the cost of just that one item. When we go to our calculators and we find C of 141, we find that that's going to be 13,765.70 minus, this is 13,720, and what we see is that's going to be $45.70. So what we see is the marginal value right here is very close to the actual cost of producing the next item. It's easier to calculate a marginal than it is to go through and find this difference here. It's just quicker. So anyway, that's how you use a marginal. It's like an instantaneous rate of change. So once you produce 140 items, your cost is changing at a rate of about $46 per item. So we calculated then the cost of producing 141 items minus the cost of producing 140, and this is actually the cost then of the 141st item. Notice what's highlighted in yellow are very similar in value. These are marginals. If you're a business major, you'll hear marginals in your economics classes, and they're talking about derivatives or rates of change. So if the rate of the change in the economy is increasing, but it's increasing slowly, the function's going up, the marginal would be positive, but the second derivative, which is the rate of change of the rate of change, would be negative. It would be slow. It's increasing slowly, as opposed to an economy that's increasing rapidly. Anyway, that's that.